Extrinsic semiconductors. In intrinsic or pure semiconductors, the carrier concentration of both electrons and holes at normal temperatures are very low. Hence, to get appreciable current density through the semiconductor, a large electric field should be applied. This problem can overcome by adding suitable impurities into the intrinsic semiconductors. The extrinsic semiconductors are those in which impurities of large quantity are present. In general, the impurities can be either third group elements or fifth group elements. Based on the impurities present in the extrinsic semiconductors, they are classified into two categories. 1. N-type semiconductors and 2. P-type semiconductors. N-type semiconductors. In order for silicon crystal to conduct electricity, we need to introduce an impurity atom such as arsenic, antimony, or phosphorus into the crystalline structure. These atoms have 5 outer electrons in their outermost covalent bond to share with other atoms and are commonly called pentavalent impurities. This allows 4 of the 5 electrons to bond with its neighboring silicon atoms, leaving 1 free electron to move about when electrical voltage is applied. As each impurity atom donates 1 electron, pentavalent atoms are generally known as donors. Antimony, Sb, is frequently used as pentavalent additive, as it has 51 electrons arranged in 5 shells around the nucleus. The resulting semiconductor material has an excess of current-carrying electrons, each with a negative charge, and is therefore referred to as N-type material, with the electrons called majority carriers and the resultant holes minority carriers. The block diagram of N-type impurity doping and corresponding band diagram is shown in figure 1. P-type semiconductors. In contrast to N-type of semiconductor, if we introduce trivalent 3-electron impurity into the crystal structure, such as aluminium, boron, or indium, only 3 valence electrons are available in the outermost covalent bond, meaning that the 4th bond cannot be formed. Therefore, a complete connection is not possible, giving the semiconductor material an abundance of positively charged carriers known as holes in the structure of the crystal. As there is a hole, an adjoining free electron is attached to it and will move into the hole to fill it. However, the electron filling the hole leaves another hole behind and is forth, giving the appearance that the holes are moving as a positive charge through the crystal structure, conventional current flow. As each impurity atom generates a hole, trivalent impurities are generally known as acceptors, as they are continually accepting extra electrons. Boron, B, is frequently used as trivalent additive, as it has only 5 electrons arranged in 2 shells around the nucleus. Addition of boron causes conduction, which consists of many of positive charge carriers, results in a p-type material, and the positive holes are called majority carriers, while the free electrons are called minority carriers.